Hello everyone, welcome to part 3 of the Lyapunov drift tutorial. Thanks for staying back and thanks for um, sticking around to attend the very last session in the whole conference this year. So in part 3, I'll talk about stochastic processing networks. So far, we talked about Lyapunov drift methods, and in part 1, I illustrated how we can use them to study queues as well as stochastic approximation. And in part 2, Zaiwei talked about how to use these results, how to use these methods to get very general results on stochastic approximation and to use them for reinforcement learning. And now I'm going to show how to use drift arguments for studying stochastic processing networks. So stochastic processing networks arise in a variety of settings. They pretty much arise in any system where there are limited resources and there are jobs that arrive at random and that need some amount of service, and they depart after getting their service. For example, in wireless networks, these jobs could be packets that need to be transmitted. In wired networks, there could be packets that need to be sent to other routers. More generally, we have such resource allocation scheduling problems that arise in cyber physical systems, in cloud computing, manufacturing systems, healthcare, call centers, transportation, data centers, and so on. So there are a variety of applications. And typically in these systems, we need to design policies, control policies, scheduling, resource allocation policies that decide which set of jobs or customers or vehicles or packets to serve at each point of time. And our goal typically is to look at things such as throughput, delay, and so on. We want to maximize throughput and minimize delay. So let's briefly talk about the performance metrics that we'll be interested in. So for any given system, stochastic processing network, one can define what is called as the capacity region. The capacity region is usually the set of all arrival rates of jobs under which it's possible to stabilize the system somehow. There exists a control policy which stabilizes the system for all these arrival rates. If you're outside this region, then for any control policy, the system is going to be unstable. The queue length is going to blow up. And one wants to design policies that maximize throughput. Such policies are called throughput optimal. All that means is that no matter which arrival rate we are given that is inside the capacity region, the system should be stabilizable under the proposed policy. So, for example, if we think of a Google data center, Google invests lots and lots of money to build these data centers. So if we come up with a policy that maximizes throughput in a data center, that means that Google is getting the best bang for buck. So Google, for example, possibly invested hundreds of millions of dollars to increase the cross-section bandwidth in their data center network by several Gbps, let's say. Then if we maximize throughput, we are making the best utilization of that additional capacity. But when we think of customers, from a customer point of view, they don't care whether Google is using their data center efficiently or not. All I care as a customer is whenever I Google for something, I want a response instantaneously, which means I care about my individual delay. So the second kind of questions that we'll be interested in is to study delay. For a given set of arrival rates, can we come up with a policy that minimizes delay? Or for a given policy, can we get a handle on how the delay behaves? And one could study things like mean delay, or we could be interested in the tails like 99th percentile or the entire distribution. And studying delays is kind of same as studying queue lengths, especially for the mean, they're related by little slow. So these are two quantities that we'll study. And indeed, we actually already looked at these things when we looked at a single server queue. So let me quickly recap what we looked at, what we discussed about a single server queue in part 1. So we considered a discrete time queuing system where time is slotted and we have arrivals that are IID, there is service and so on. And we said that the queue length evolves as follows. Future queue length is the current queue length plus arrivals minus departures. And there's a bracket plus to ensure that the queue length doesn't go negative. S is the potential service. And if there are no customers, there'll be unused service, and that's taken care of the bracket plus. Or we can write the unused service explicitly by introducing a new variable, which depends on everything. It depends on Q, A, and S. And we said that the understanding the behavior of this unused service is very important in studying queuing systems. And in particular, due to its definition, we have QK plus 1 times UK is 0. Whenever unused service is positive, QK plus 1 is 0. And the first question is about throughput. So one can ask, what is the maximum possible throughput in a queue? And the answer is that mu. It's a service rate mu. As long as lambda is less than mu, it's stable. Otherwise, it's unstable. And we proved this using Foster-Lyapunov theorem and using quadratic Lyapunov function in part 1. Then the next question is, can we characterize the mean delay, mean queue length, or the distribution of queue length? And the answer is no. That in general, one cannot find a closed form expression for queue lengths or delays. If one looks at special cases such as Bernoulli arrivals, Bernoulli service, and so on, there are closed form expressions. But for general arrivals, there are no closed form expressions. And that motivates asymptotic study. And we looked at heavy traffic limit in part 1, where we are pushing the system close to its capacity. We're letting lambda approach mu. Or in other words, if epsilon is mu minus lambda, we're letting epsilon go to 0. And then we said that the queue lengths in this case blow up, and they blow up as of the order 1 over epsilon. And so we looked at queue length multiplied by epsilon, and we said that its mean in the limit as epsilon goes to 0 does not depend on the whole distribution. It depends on just the variances of the arrival and service process, and it's just the average of these two variances. And we proved this using a drift argument. We picked a quadratic Lyapunov function and set its drift to 0. Then we also studied the distribution of epsilon q. Epsilon q is a random variable. Instead of its mean, I want to understand the whole distribution. And the distribution converges to an exponential with this mean. And we proved this using an exponential Lyapunov function. And to do this, the key step was in generalizing this QU equal to 0 equation. And we did this by writing it in this exponential form, which was kind of like a simple trick because we can prove this in one line. So in all of this discussion, unused service played a very important role. In this part, I'm going to use these same ideas, Foster-Lyapunov theorem for stability and then drift arguments to study mean queue length and distribution in the context of more general stochastic processing networks. And we'll see that unused service will play a very important role as we do this. And we'll do this by studying a representative example of the stochastic processing networks, which is an input queued switch. Let me first start by explaining the motivation and the model of an input queued switch. So today we have mobile phones and we have all kinds of apps which are quite powerful. And most of these apps are powered on the backend by a cloud, by data center. And most of the web apps are also powered by data centers. So cloud computing and mobile app revolution is supported by cloud computing data centers. And typically these data centers have hundreds of thousands of servers. And these servers in addition to processing and RAM, they also have storage, and they store all kinds of things, data in all forms, web pages, databases, audio, video files, pictures, documents, and so on. And whenever there's a request, for example, I open my Facebook, then there's a server that is serving me, and this server has to reach out to many other servers in the data center to collect data about all my friends so that it can show me my newsfeed. And this data is spread out all through the data center. And this server that is serving me has to reach out and talk to all the other servers. And this is enabled by what is called as a data center network. And design and operation of this data center network is a fairly challenging problem. And efficiently running it is essential given the size of today's data centers. So the big question that we are interested in is the following. Are there low complexity scheduling algorithms? So as the servers are trying to talk to each other, there are a lot of packets that are going back and forth in the data center, and we need to schedule these packets on the network. So are there scheduling algorithms that have low complexity? Why low complexity? Because given the size and the speed of these networks, we need to be able to make these scheduling decisions very, very fast. And these algorithms should result in small packet delays. Or maybe I'll go one step further, and then I'll ask, is it possible to design scheduling algorithms which have delays that don't scale with the size of the network? No matter how large the network is, I want the delay to be constant. And in this talk, we'll see that the answer is yes in the heavy traffic regime. So what is a data center network? Typically, when you look at a data center, the servers are arranged in racks. and each rack has a top of the rack switch that connects all the servers within that rack and also connects them to other servers in the data center. And this top of the rack switches are connected to a next tier of switches, which in turn are connected to the highest tier, which is the core switches. So essentially, we have a tiered architecture. But we can abstract, for the purpose of this talk, we can abstract away all these details and then approximate this network by a switch. Because when people design these networks, the goal is to make it as close as possible to a giant input queue switch. So what is a switch? We can think of the switch as, if there are 100,000 servers in a data center, we can think of it as a 100K cross 100K switch, where each server appears both on the input and output side. And at each time, each input can be connected to exactly one output. So you can think of it as so that the server can communicate to, each server can communicate to exactly one other server. So more abstractly, we can think of a switch as a matrix of queues. So the inputs correspond to rows and the outputs correspond to columns. And at each input, let's say I'm looking at this input server, it maintains a separate queue for packets that want to go to each of the outputs. So there are n separate queues in each row, and similarly n for each column. And packets arrive into these queues according to an IID random process. So suppose there's a packet that arrives to the first input that wants to go to the second output, then we pretend that it arrives into the second queue, this particular queue. And each packet needs exactly one time slot of service. This is a discrete time system. And then after it has its service, it just disappears from the system. The key constraint is that at each time, in each row, at most one queue can be active, because each input server can be connected to at most one output server, and vice versa. In each output server is talking to at most one input server, which means in each column, at most one queue can be active. Which means if we look at the maximal schedules, we have a permutation matrix. So at each time, we have to pick a permutation matrix. And this is the scheduling problem in a switch. And the goal is, how do we keep picking these permutation matrices in each time slot to minimize delays, maximize throughput, and so on. So we can rephrase the goal from 2 slides ago by saying, are there low complexity switch scheduling algorithms that maintain small delays that don't scale with the size of the switch? So a natural question in this context is, I started off the talk by talking about general stochastic processing networks, and then now I'm focusing on switch, and I'm going to present results mainly for a switch. And why is this? So there's a quote that is usually attributed to Einstein, which says that whenever one is thinking about a problem, one should make it as simple as possible and not any simpler. So if one wants to understand stochastic processing networks, the simplest non-trivial example is a switch. In fact, this is a quote from a paper by Devavrat Shah and John Tsitsikalis, where they say that input queue switches are the simplest non-trivial example of a stochastic processing network. And over the years, input queue switch has served as a guiding example for designing as well as analyzing scheduling policies. So we hope that making progress on it will lead to further advances in the performance analysis of more general stochastic processing networks. So this motivates our study of an input queue switch. So if you recall, in a single server queue, we started with the capacity region, and then we went on to talk about the mean queue length and the distribution of queue length. We'll follow pretty much the same outline in a switch. So we'll start with the capacity region. So there are n square queues in a switch in the matrix. And let's say lambda ij is the arrival rate for the queue in ith row and jth column. And one can show that the maximum supportable set of arrival rates should satisfy these two inequalities. Remember, in each time slot, in each row, I'm serving at most one packet. Therefore, for stability, the total arrival rate into each row should be less than 1. And similarly, the total arrival rate to each column should be less than or equal to 1. And these constraints essentially form a polytope in n squared dimensions. N squared dimensions because we have n square variables, and we have 2n constraints here. Good. So in this talk, the algorithm we'll focus on is the MAXWEIGHT algorithm. And remember, the goal is to find a permutation matrix in each time slot. And in MAXWEIGHT, At each time slot, one picks the permutation that has the maximum weight, where the weight corresponds to the sum of the Q lengths in that permutation. So let's see an example. Let's say this is a 3x3 switch, and these are the Q lengths at the current time. There are 5 packets waiting in this queue, and 4 in this queue, and so on. And now, since this is 3x3 switch, there are n factorial permutations, 3 factorial, which is 6 permutations. I show all the 6 permutations here, where the blue queues highlight which queues are in service. And for each permutation, I calculate its weight. So for this permutation, the weight is the sum of these 3 diagonal queues. 5 plus 1 plus 2 is 8. For this queue, it is these 3 queues. So it is 4 plus 2 plus 1, which is 7, and so on. Now, among all these 6 queues, the maximum weight is 9 that corresponds to this schedule. So we go ahead and schedule those particular queues. So the many advantages of MAXWEIGHT. The first one is that it has polynomial time complexity. It has n power 2.5 complexity, and it can be implemented without knowing the arrival rate. At each time, I just look at the Q lengths, find the maximum weight matching, and so on. Even though n power 2.5 is not too large, given the size of today's data centers, it may be prohibitively expensive. So we have another piece of work, which I'll not talk about today, where we propose a large class of algorithms which have much lower complexity than MAXWEIGHT, and then show that they have pretty much the same behavior as MAXWEIGHT. So the first question is MAXWEIGHT throughput optimal? Which means given any arrival rate in the capacity region, where the row sums and column sums of the arrival rate is less than 1, can MAXWEIGHT stabilize the system? And the answer is yes. This was proved basically in the 90s. And one essentially uses the same idea as in a single server queue. One uses a quadratic Lyapunov function and applies Foster-Lyapunov theorem to show throughput optimality of MAXWEIGHT. And the quadratic Lyapunov function is Q square, norm square, 2 norm square. So Q is this matrix of Qs. We think of, even though I represent everything as a matrix, I interpret it as simply an n square dimensional vector. So it's just a L2 norm, basically sum of the squares of all the Q lengths. And one can use the same Lyapunov function, set its drift to 0, like we did in a single server queue. Then we should get a bound on the main Q lengths. And indeed, that is the case. We'll again see that the sum of all the Q lengths blows up as 1 over epsilon, and where epsilon is the distance to the boundary of the capacity region. And if I multiply it by epsilon and look at the limit, I'll get a bound that is n square, order n square. N is the size of the switch. N square is the number of Qs that we have. But it turns out that this bound is loose. So the key question is, can we get tighter bounds? And before I answer this question, I have to actually be more precise about defining the heavy traffic limit. So intuitively, it means that we approach a point on the boundary of the capacity region. In the single server queue, it was very simple. We just make lambda as close as possible to mu. But here, since we have so many mu's on the boundary, which one do we approach? That's the question. And in particular, there are 2 kinds of points on the boundary that we can approach. So remember, the capacity region is an n square dimensional polytope. So it has many, many faces. It has this full faces, which are called facets, which are n square minus 1 dimensional facets. If you think of it as a cube has faces, planes, and then it has edges. So if you're up the faces, the 2-dimensional faces of a cube are facets, the edges are lower dimensional faces. So if you're approaching a facet, then we call it, we say that the complete resource pooling condition is satisfied. But if we approach intersection of several facets, which means we are approaching a lower dimensional face, or in the context of a cube, we are approaching either an edge or like a corner point, then we say that the complete resource pooling is not satisfied. And then these 2 cases should be studied separately because there's a qualitative difference in the behavior of Q lengths in these 2 cases. To understand why, let's first consider why do people look at heavy traffic regime. One reason is that the analysis becomes more amenable in heavy traffic, and the reason for that is state space collapse. So the queuing system, the switch system, is an n square dimensional queuing system. There are n square queues, but in the heavy traffic, this queuing system behaves as if it lives in a lower dimensional subspace, as if it has a lot fewer number of queues. So let's first consider the case of complete resource pooling, where I'm approaching a point on the interior of a facet. Here, the n square dimensional Q length, the state of the system, collapses onto a line which is simply the normal vector of this facet. And in a switch, saying that you're in the interior of a facet means that exactly one of the constraints is tight. Remember, we have two n constraints. Each row is less than or equal to 1. Total arrival rate for each column is less than or equal to 1. Among these two n constraints, exactly one is tight in heavy traffic. All the others are loose. So each constraint corresponds to either a row or a column. So without loss of generality, we'll just assume that the first row is tight. So the total arrival rate in the first row is 1 minus epsilon. So it's approaching 1 as epsilon goes to 0. For all the other rows, the total arrival rate is approaching some number strictly less than 1, like half or 0.7 or whatever. For each column also, the total arrival rate is approaching a number strictly less than 1. So this corresponds to the complete resource pooling setting in a switch. And in this case, the n squared dimensional switch essentially collapses to one dimension. So it behaves as if it is basically a single queue. And we'll see more details about it as we go along. Now, if we approach a point that is at the intersection of multiple facets. So in this picture, this is a facet, this is a facet. We are approaching a point at the intersection of the multiple facets. Then there is no unique normal vector. In fact, there is a normal cone. So here we should take a normal vector of this facet, normal vector of this facet, and then there's a cone spanned by them. And then one can show that the Q length vector in this case actually collapses to this cone. So we don't have a single dimensional collapse. So in the context of switch, the not satisfying complete resource pooling just means that more than one, either two ports are saturated or more, two or more ports are saturated, which means among these two n constraints, two or more are tight. For simplicity, for most of this talk, I'll focus on the case where all the constraints are tight. Basically, all the rows are approaching 1. So all the rows, the total arrival rate of each row is 1 minus epsilon. Total arrival rate for each column is 1 minus epsilon. All rows and columns saturate. Towards the end, I'll talk about the setting where when only a subset of rows and columns saturate. So in this case, because I collapse into the cone, my state space it's still collapsing, but not into a one-dimensional subspace, not onto a line. And when all rows saturate, the n squared dimensional switch collapses into a 2n minus 1 dimensional subspace, which means these n square queues behave as if there are only 2n minus 1 queues in reality. And we'll see more details about this. We'll see why 2n minus 1 arises. And this 2n minus 1 is the dimensionality of the subspace into which collapse happens. So with that motivation, let's first focus on the setting when there is no complete resource pooling, in particular, when all rows and columns saturate. After this, I'll talk about the case where a single row saturates. And after that, I'll conclude the talk. OK, so like I mentioned, each row, the total arrival rate for each row and for each column is 1 minus epsilon. And we are interested in understanding what happens in heavy traffic, that is as epsilon goes to 0. And we are interested in the delay. How does the delay, the heavy traffic delay, scale with the size of the switch n? And it was conjectured long ago that if I look at the sum of the Q lengths and multiply by epsilon and take the limit, the answer is order n. Remember when I used Q norm square as Lyapunov function, then I got order n square. So that's why that was loose. So the conjecture was that this is order n. Or to understand better, so the sum of the Q lengths in heavy traffic are of the order n over epsilon plus some little of 1 over epsilon terms. So we essentially proved this conjecture a few years ago, and that is, I'll state the result now. So before I state the general result, I want to first state a simpler case. Suppose we have uniform traffic and this traffic is Bernoulli, which means the arrival rate of all the queues is equal. Since the row sum and column sum is 1 minus epsilon, each arrival rate should then be 1 minus epsilon divided by n. Further, let's say that the arrival process is Bernoulli, which means for each queue, independent of everything else, in each time, there is a packet arrival with this much probability, 1 minus epsilon over n, and with the remaining probability, there's no arrival. And we are interested in the heavy traffic regime as epsilon goes to 0. So we proved that in steady state, the heavy traffic scaled sum of Q lengths, heavy traffic scale simply means I multiply by epsilon, the mean sum of Q lengths, is we have an exact expression for this, not just order. It's exactly equal to this expression n minus 3 over 2 plus 1 over 2n. This expression looks like weird, and to interpret it, it's convenient to write it in this form: 2n minus 1 and then half and 1 minus 1 over n. This 2n minus 1 corresponds to the dimension of state space collapse, because we are collapsing into 2n minus 1 dimensional subspace. This 2 is the same 2 we had in the single server queue. Remember, the queue length of a single server queue converges to the sum of variances divided by 2. So this is the same 2. And this 1 minus 1 over n is simply the sum of the variance for each row. Like if you look at the variance of this guy and then add it up over the whole row, we essentially get 1 minus 1 over n. Then using Little's law, we can find the average delay in a switch, which is simply obtained by dividing this by total arrival rate, and that's order 1. And this is what I promise, that the average delay does not scale with the size of the switch. Now let me say the more general result. So we don't need to assume a uniform arrival rate. We don't need to assume Bernoulli traffic, but we do assume that all the rows and columns are saturated. Then we show that the same quantity, expected sum of Q lengths, multiplied by epsilon in the limit, converges to 1 minus 1 over 2n, which is essentially 2n minus 1 divided by 2n, times sigma square. So you interpret the sigma as a matrix, and it's the 2 norm of it, or it's simply the sum of all the variances. So this essentially means that the sum of Q lengths is of the order this guy divided by epsilon, plus some little o terms. This result was proved 4 years ago. More recently, we have a refined result where we show that the first order term is exactly the same. It's 1 minus 1 over 2n sigma squared divided by epsilon. The second order term, which was little of 1 over epsilon, we show that it's actually of the order log 1 over epsilon. So the question is this log 1 over epsilon? So it is not 1 over epsilon square, or it's not even polynomial, it's logarithmic, which means this is pretty accurate. The first order approximation is pretty accurate. Then the question is this log tight? Or can one actually obtain a constant error with respect to the 1 over epsilon term? So in the case of single server queue, the heavy traffic approximation error is actually a constant. So here at this point, we don't know. This is still open. It's still open to find out whether this log is tight or not. OK, so that's the result. Let's now talk about the intuition behind the state space collapse. So remember, we are assuming that the total arrival rate to each row is 1 minus epsilon. Total arrival rate to each column is 1 minus epsilon. There are 2n equations here, one each for each row, one each for each column. I can write these 2n equations in this form using dot product notation. As epsilon goes to 0, the right hand side is simply 1. This guy is the sum of the ith row, sum of all the arrival rates in the ith row. I can think of it as dot product of the lambda vector, which is a matrix, with EI vector, which is a matrix where the ith row is 1 and all the others are 0. So when I take the dot product, I essentially get the sum of the ith row. Similarly, so I have n of these guys. There is a EI vector matrix for each row, so the n of them. And then I can define EJ tilde matrix for n of them, one for each column, where the jth column is all 1s and all the other guys is 0. When I take dot product of lambda vector with this, I'll get some of the arrival rates of the. OK, so now if we think of the capacity region, which is a polytope, these guys are essentially the equations. These 2n equations are the equations of the facets. And the e's and e tildes are the normal vectors of these facets. And essentially, in the limit, we are approaching a point that's at the intersection of these 2n facets. And so the arrival rate lies at the intersection of all these facets. And so the collapse happens to the cone spanned by these 2n vectors. And notice that these 2n vectors are not linearly independent. If I take all these e's, n of them, and add them up, I'll get all 1s matrix. If I take all the e tildes, n of them, and add them up, I'll get all 1s matrix, which means I have one equation that's satisfied by all these e's and e tildes. Therefore, they're not independent. One can show that the space they span has dimensionality 2n minus 1. The 2n minus 1 independent vectors among these 2n vectors. And that's the reason the collapse is into a 2n minus 1 dimensional subspace. Within that subspace, it's the cone spanned by these 2n vectors. So pictorially, if you think of these as the facets, the 2n facets intersecting on these lower dimensional face on this edge, and then take all the normal vectors and you get the cone spanned by them. This picture is not accurate because I have to show you an n square dimensional picture. If n equal to 1, you get a single server queue, so it's not interesting. N equal to 2 is the non-trivial interesting example. And if n equal to 2, we are in 4-dimensional space. Unfortunately, my version of PowerPoint does not support 4-dimensional pictures. It can only draw like 3-dimensional pictures. So I'm showing just a fake picture. This is not a real capacity region of a switch. OK, cool. So any vector in the space, in this cone, sorry, can be written as a conic combination of these ETs and detailers, which means that it's a linear combination where the weights are non-negative. Why do we have collapse into this particular cone? One intuitive way of thinking about it is that you have these n factorial matchings. At each time, you can find all their weights. You find the maximum weight matching, and then by serving it, you're decreasing it. And when you're decreasing it, other matchings are also decreasing because these matchings share same set of queues. But it turns out that by decreasing the largest matching, we're essentially trying to equalize all the queues. And in heavy traffic, we're trying to equalize all the matchings. In heavy traffic, if I were to ask, what are the set of weight vectors, n square dimensional weight vectors, which have the property that all n factorial matchings have the same weight, it's exactly this cone. So that's the reason. So basically, MAXWEIGHT is trying to equalize all matchings, and that's why it collapses to the region where all matchings have same weight, and that's exactly the score. How do we prove the state space collapse result? If I represent a cartoon of the cone simply like this in 2 dimensions, and if this is my Q length vector, which lives in n square dimensions, I can define the parallel component of this Q onto the cone by projecting this Q onto the cone. And I can look at the error, and the error is defined to be the perpendicular component. So essentially, we want to show that Q is approximately equal to Q parallel. And the way we show this is as follows. Remember that in a single server queue, the Q length is of the order 1 over epsilon in heavy traffic. One can similarly very easily show a lower bound. The Q length should blow up as 1 over epsilon, which means as epsilon becomes smaller, the Q length becomes larger. But if we look at the Q perp, that does not change. It can be upper bounded by constant. It can change, but it can be upper bounded by constant, which means as epsilon becomes smaller and smaller, Q parallel is becoming larger and larger. It's going to infinity. But Q perp is a constant, which means that Q perp is negligible compared to Q parallel. So in that sense, Q is essentially in this cone. More precisely, the mathematical statement that we prove is the following. Take this Q perp vector and take its norm and true norm. And if I look at any moment of this guy is a random variable. If I look at any moment of it, I can bound it. Each moment can be bounded by an appropriate number. And this number does not depend on epsilon. As epsilon goes to 0, this does not blow up to infinity. It depends on other parameters, but not epsilon. And how do we show this? The only way we know of showing bounds like this is by setting drift equal to 0. And that's essentially what we do. But and the Lyapunov function we use for this purpose is Q perp square. By using Q perp square as Lyapunov function, we can bound Q perp. But then for the proof, just bounding Q perp alone is not enough. We need to bound higher moments as well. At least 1 plus epsilonth moment. I don't really care about all the moments, but I need something more than 1. So for that, in addition to just setting the drift of Q perp square to 0, we actually exploit a known result from Hayek in the 80s, which can be thought of as a variant of Forster-Lyapunov theorem, which gives bound on all moments. And in fact, if one looks at the proof of this Hayek's lemma from the 80s, it again depends on using an exponential Lyapunov function. So equivalently, I can say that we get all these results by working with e power Q perp as a Lyapunov function. Or we use Q perp square as Lyapunov function and plug it into Hayek's lemma. Okay. Now, once we have this state space collapse, my goal again is to bound Q lengths, mean sum of Q lengths. And to do this, I again use a test function and set its drift to 0. And the test function I use is Q parallel square, the projection onto the cone. Actually, here I don't project onto the cone, I project onto the space. If you want, you can project onto the cone, but projecting onto the space is easier because it's a linear operation, but projecting onto the cone is not a linear operation. For state space collapse, we had to work with the cone, but for this, to get the bounds, heavy traffic, to get the exact heavy traffic expression, it's enough if we work with the space, because essentially the difference between the space and the cone is fairly small, so to say. So here the projection is onto the space, and then we take Q parallel square as the Lyapunov function and set it equal to 0. When we set Q square Lyapunov function to 0 in the case of a single server queue, we expanded it in terms of binomial theorem, and we had to handle the unused service terms. Here again, we're going to have a similar challenge. The key challenge in working with this Lyapunov function is in handling unused service terms. Essentially, we need to handle a term that looks like this: Q parallel dot product with U parallel. In the case of a single server queue, we know that Q times U is 0. This is Q parallel K plus 1 at time K plus 1 times U parallel at time K. And the whole point of state space collapse, the reason we establish state space collapse, is to show that this guy is equal to 0. And we do this by essentially using Cauchy-Schwarz inequality. And then since we have bounds on perp of Q length, we use that to show that this term is negligible. Once we show that that is the crucial step, once we show that step, everything else is like simple, straightforward manipulation, and we get the result that I stated before. Okay. Now I'm going to talk about the setting. So I said that when complete resource pooling is not satisfied, we have more than two or more ports that are saturated. So far, I looked at the case when all ports are saturated. Now let's look at the setting when a subset of rows and columns are saturated. So there are NR rows, the first NR rows, and NC columns, the first NC columns, where the total arrival rate approaches 1 in the limit. It's equal to 1 minus epsilon. But for the other rows and other columns, it's approaching some number strictly less than 1. So the fact that I'm looking at first NR rows and first NC columns is without loss of generality. If NR is equal to 1 and NC equal to 0, this corresponds to complete resource pooling setting, and that's included in this slide. But in the slide, I'm not including the setting when NR equal to N and NC equal to N, which is the completely saturated setting in the previous slide. Okay, so we have general results again for this setting for any general arrival. But for simplicity, let me state in the case of a special Bernoulli uniform arrival. What I mean uniform here is that the arrival rate for these queues, arrival rate of all the red queues, these guys within the small square, and the orange guys, these guys. So basically arrivals of all the queues in the first NR rows and all the queues in the first NC columns. Pretty much in this picture, only this yellow queue is excluded. For all these guys, the arrival rate is Bernoulli 1 minus epsilon over n. And for the yellow queues, it's something that's strictly smaller than 1 over n in the limit. And this ensures that the row sum and column sum for these rows and columns is approaches 1. Then the limit of sum of the Q lengths multiplied by the heavy traffic parameter approach is under max weight is exactly equal to this. It's NR plus NC times 1 minus 1 over n divided by 2. So the 2 is the same 2 that we have in single server queue. The 1 minus 1 over n is the variance of each row or column for the Bernoulli arrival. And NR plus NC is the number of equations that are tight. So this is the dimensionality of the state space collapse. So if you think of the polytope, we are approaching a point on the boundary that's at the intersection of NR plus NC facets. So the collapse will be into a cone that's normal to these NR plus NC facets. And these are all independent. These are all linearly independent constraints as long as NR and NC are strictly less than N. And so the collapse is into NR plus NC dimensional space. If both of these NR and NC are N, then they would be dependent and the dimensionality is 2n minus 1. In that case, we should not have n plus n, which is 2n, but we should instead have 2n minus 1. That's what we had in the previous completely saturated setting. So one of the key takeaways so far is that the heavy traffic behavior depends on the number of constraints that are tight, which is basically the number of facets that are intersecting at the point that you're approaching on the boundary, and that determines the region, the dimensionality of the region into which collapse happens. In this case, that is NR plus NC. So the key takeaways so far are that first step is to establish positive recurrence stability, throughput optimality within the stability within the capacity region, and we do this using Foster-Lyapunov theorem. And the Lyapunov function we used was Q norm square. And using that Lyapunov function, we get loose Q length bounds. But to get tight Q-length bounds, we ended up using Q parallel square as the Lyapunov function. And to work with this Q parallel square as the Lyapunov function, we had to establish state space collapse. And to do that, we in turn used Q perp square as the Lyapunov function. So very interestingly, we ended up using Q square for stability, while directly using it as loose. If I split it into two parts, Q perp square and Q parallel square, so Q square is equal to Q perp square and Q parallel square because of Pythagoras theorem. If I split it into two parts and work with each of them separately, we end up getting the tight bounds. And this tight bounds, the correct answer, the sum of the Q-lengths is essentially proportional to the number of constraints that are tight. And the key ingredient as we go through all of this is again understanding unused service. In the case of single server queue, we had a nice equation qk plus 1 times uk equal to 0 that generalized into something that looks like this. Dot product of q parallel and u parallel is approximately equal to 0. So in a single server queue, there's no expectation at every time this is equal to 0. For a switch, we establish this only under expectation in steady state. And even in that case, this is not exactly equal to 0. It's approximately equal to 0. OK, so this is these are the results we have so far for the case when we don't have complete resource pooling. Now let me talk about the case when there is complete resource pooling. So again, remember in the switch, this corresponds to the case where exactly one constraint is active. So I'm assuming without loss of generality that it is the first row. So the total arrival rate in the first row is 1 minus epsilon. So it's approaching 1. And all the other rows and all the other columns, the total arrival rate is approaching a number strictly less than 1. So if I look at the mean sum of Q-lengths, I can plug and play into the result that I presented a few slides ago. I presented the result where NR rows and NC columns are saturating. I can set NR equal to 1, NC equal to 0. I can plug in that result. There I stated it only for Bernoulli arrivals, even though I said that we have a general result. Here I'm actually stating the general result when a single row saturates. And the answer is half times NR plus NC is just 1. So it's just half here. And the variance term is sum of the variances only of the first row. I don't care about everybody else. Only look at the variances of the queues that are saturating and some of those variances. OK, so again, remember, in this case, state space collapses onto a line which is normal to the facet that we are approaching. So when the state space collapses to a line, the system essentially behaves like a single server queue. So it's as if all the resources in the system are pooled into a single server, a giant server, and that giant server is serving all the queues in this row. Whereas all the other queues are not saturating, so they don't even matter in heavy traffic. That is why this is called complete resource pooling. It's as if I'm pooling all the resources into one giant server that's serving the first row. So in this case, the collapse is onto this normal vector, and this normal vector is basically the E1 vector, because I can write this equation as lambda dot E1 equal to 1, where E1 is the vector with ones in the first row and zeros everywhere else, which means the Q length is along this line in the limit, which means this Q length vector is such that all the other rows are negligible in heavy traffic, which means if I multiply by epsilon, all the second row, third row, and so on, in the limit they vanish. Only the first row does not vanish. And even in the first row, all the queues should be equal. Which means putting these two together, putting the fact that I have the sum of all the Q lengths in heavy traffic, and also the fact that this epsilon times Q is along this line, which means that all these guys are 0 and the first row is equal, I can find the limiting behavior of each and every individual Q length multiplied by epsilon. Indeed, it's going to be 0 for all the queues outside the first row. And for the first row, they're all going to be equal, the n of them. So all I do is I take this formula, divide by n, put an n in the denominator. So I didn't do anything new so far. I just took the result that I showed before, but then applied it in the context of complete resource pooling. When you don't have complete resource pooling, when multiple rows and columns saturate, even though we have an expression for some of the Q lengths, you cannot get individual Q length. If you have symmetry, that's a different case. By symmetry, you can argue they should all be equal. But if you don't have symmetry, you cannot get individual Q lengths. However, here, because of complete resource pooling, the system is inherently simple. Essentially, it's a one-dimensional thing, so you can pretty much argue everything about it. But in a multi-dimensional system, it's more intricate. It has more complex behavior. And because of the simplicity, we're able to get exact Q lengths. So then so let's actually talk about state space collapse in this context. So I said that the collapse is along this vector where all the first row is all ones, everybody else is zero. Let's focus on the first row alone. So the state space collapse is essentially saying that all the queues in this row are becoming equal. Why is this? So let's think of max weight. What is it doing? It's picking the matching with the maximum weight and serving it. And now in heavy traffic, all these other rows are irrelevant. So now we are only interested in the first row. First row, the queues in the first row alone are large, which means when it's picking a matching, it has to pretty much only care about the first row. And remember, in the first row, only one queue can be active at each time, which means at each time you're picking a queue in the first row that is pretty much the longest. So essentially in the first row, you're picking the longest queue and serving it. And by doing it, you're decreasing it. And among all these n queues, if you always keep serving the longest queue, then these guys will become equal. And that's essentially what is happening. This is the intuition for state space collapse. And in terms of proving state space collapse, we follow the same methodology as before. But earlier I had a cone. Now I just have a line. So life is even simpler. That's why this result was known a lot earlier than the result in multidimensional setting. This was first proved by Stolyar in 2005. So again, I work with the Q length vector. I project onto the line. I call that Q parallel. Here I can write the exact expression for this Q parallel. And then I look at the error Q perp, and then I show that all the moments of this Q perp are bounded. And I do this using Q perp square as Lyapunov function and invoking Hayek's lemma. OK, if we think of a single server queue, the first question was about stability. Second question was about mean heavy traffic behavior of mean queue length. And the third question was about the distribution of the queue length. So I can ask the same thing here. Now I know in the multidimensional setting, I did not even know about the individual queue lengths. So distribution is kind of out of scope at this point. But here I know all the individual mean queue lengths. And I know that they're all equal in the first row and zero otherwise. So I can ask what is the limiting joint distribution of the queue lengths. And we know that epsilon q essentially lies in this is proportional to this vector. It lies along this vector, along the line spanned by this vector. So the theorem is that epsilon q, which is a random vector, it's an n squared dimensional random vector. It converges in distribution as epsilon goes to 0 to a n squared dimensional random vector, which is essentially this. All these components are 0. These components are all equal, which means they're coupled random variables, and the marginal is exponential. So essentially what I'm saying is that each of these Q lengths converts to an exponential random variable with the right mean, with this mean, and all the Q lengths are equal. They're not independent, they're opposite of independent, they're coupled, they're all equal. If I tell you that this Q length is like 256, then this Q length is also very, very close to it. So this is very much in spirit like a single server queue. But it takes the exponential behavior of a single server queue and combines it with the state space collapse behavior that we get due to max weight and so on. So let me very briefly talk about the proof. This can be thought of as the intuition behind the proof for both the mean calculation as well as the distribution calculation. So remember, in a single server queue, the key thing is the unused service. And the unused service is essentially determined by this equation qk plus 1 times uk equal to 0. And but the thing is, when you have multiple queues, if I take qk plus 1 of one of these guys, let's say of this guy, and then multiply it with the unused service of some other guy, the product need not be 0. Because it is quite possible that one of these queues has unused service because it's empty, whereas the other queue is non-empty. That's why this product need not be 0. If I multiply q and u for the same queue, of course it is 0. That's true for any queue. So this is our major challenge, because our Lyapunov function q parallel square is essentially like so in the case of this one-dimensional collapse, q parallel is essentially like sum of all the queues in the first row. So when I take that, its square, and then expand it out, I'll get cross terms. I'll get cross terms of multiplying one queue length with the other unused service. But because of state space collapse, all these cross terms are 0. So because of the state space collapse, the sum of the queue lengths in the first row essentially behaves like a single queue, like a single server queue, which means the sum of the queue lengths in the first row multiplied by the sum of all the unused service in the first row is approximately equal to 0. Why is this true? So when you expand this, you'll get qj uj term, which is 0 by definition of a single server queue. And then you'll have cross terms which are problematic, qi times uj. But because of state space collapse, all these queues are essentially equal. So I can pretty much approximate this qi by qj. Then you get qj uj, which is essentially equal to 0. This in matrix notation, vector notation, gives us q parallel dot product with u parallel is equal to 0. So even though this is an intuitive argument, all of this can be made precise using Cauchy-Schwarz inequality and the moment bounds that we have in state space collapse. And this plays a key role in using q parallel square as Lyapunov function and getting the mean q lengths. Then I showed you the distribution. How do we get the distribution? In a single server queue, we set exponential Lyapunov function to 0, drift of exponential test function to 0. And then we generalize this qu equal to 0 to this form, e power q minus 1 times e power u minus 1 to 0. So here, to get the distribution under complete resource pooling, we need to do essentially the same thing. My Lyapunov function is e power summation q. Summation q is essentially like q parallel. And I set its drift to 0. And to work with this, I need a generalization of this e power q minus 1, e power u minus 1 equal to 0. And that essentially is the same thing with q replaced by some of the q's in the first row, u replaced by some of the u's in the first row. And the intuition for this is same as before. Using this and setting this drift to 0, we get the convergence in distribution. So to summarize the results that we have so far, we looked at a single server queue in part 1. We used q square as a test function. We used q times u equal to 0, the definition of unused service. And we showed that the heavy traffic limiting q length multiplied by epsilon converges to the average of variances. Then again in part 1, we showed that epsilon q in distribution converges to an exponential random variable with this mean. And we did that by working with an exponential test function. And we generalized this qu equal to 0 to e power q minus 1 times e power u minus 1 equal to 0. In this part, when we have complete resource pooling, when the collapse is onto a line, we showed that we calculated all the individual mean q lengths. And we said that they're 0 except in the first row. And in first row, we have an exact expression for that. And we did this using q parallel square as Lyapunov function, which is essentially sum of the q's in the first row whole square. And we showed that qu equal to 0 essentially generalizes to something of the form summation q times summation u is approximately equal to 0. This should be an expectation. This is true only in expectation. And I also talked about getting the distribution. We calculate the limiting distribution of epsilon q, which is a random variable where, again, rows 2 and forward are 0. First row, everybody's equal and they're all exponentials. And we did this using e power theta epsilon summation q as the Lyapunov function, which is essentially, again, e power theta norm of q parallel. And then we again generalize this exponential qu equation into this context by putting expectation appropriately. Here it's not quite 0, but it's small enough. It is little of epsilon square. When we divide by epsilon square, it vanishes. And that's good enough. And we also talked about the case when we don't have complete resource pooling. We looked at the case when a subset of rows and columns saturate, and also the case when all rows and columns saturate. When all rows and columns saturate, we showed that the sum of all the q lengths is 1 minus 1 over n, 2n times sigma square. We don't have individual q lengths. And we showed this again using q parallel square as Lyapunov function. But now this q parallel is projection onto this cone or the space appropriately defined. For state space collapse, it was the cone. For upper bound, it was the space. For the q length bounds, it was the space. And a natural question is the remaining rows of this table, remaining cells of this table. What is the joint distribution of epsilon q? This is a major open problem in the space, and we are working on it. We don't quite have an answer, but at least we have a candidate. So hopefully we'll have a paper out on this very soon. So to take a step back, I started this part by motivating with general stochastic processing networks. So there are many kinds of stochastic processing networks. So all the examples that I talked about in wired networks, cyber-physical systems, call centers, and so on, can be modeled by like a queuing system. It could be a simple single server queue, or it could be a bunch of single server queues, but they could be correlated in some manner. Maybe the arrivals are correlated, or the service is correlated. Or maybe you have a bunch of single server queues, but the arrivals are correlated because of your choice. So you have a single stream of arrivals. You get to choose which queue you send them to. And then you have to do this to minimize delay. This is called the load balancing problem. So you control the arrivals and your control introduces correlations across these queues. Or maybe the arrivals are independent, but you have a control on the service. So there are a bunch of queues and you don't quite have enough servers. And then maybe you have to use limited resources to serve these queues and you have to do certain amount of scheduling. This is essentially the switch problem falls into this setting. There are n² queues. At each time, you only can serve n queues, and these n should form this permutation matrix. And the question is, how do you do that? So this introduces correlation across the servers, and you have to come up with a scheduling problem. Or you could have, you could imagine a single queue and there are multiple servers and these servers maybe only, and they are all serving that single queue. Or you have a bunch of queues, a bunch of servers need not necessarily the same number. And there is a graph that denotes which server can serve which customer. And at each time you have to, the server gets to pick which customer it can serve among the compatible ones. And you have to come up with a scheduling policy to minimize the delay. This is called a parallel server model. This is just a subset of the kind of queuing models that arise. There are even more general models where the service rate actually depends on some exogenous random variable that arises in wireless networks. Because of fading, the capacity of each wireless link varies with time in a random manner. And all of this, so instead of looking at all of this, I simply focused on one particular model on a switch. And I motivated that by quoting from Devavrat Shah and John Cicillis saying that it's the simplest non-trivial example. Now that we understand this switch behavior reasonably well, I know we have some parts that are open, but at least we have most of the table covered up. The question is, what does that imply for all these other stochastic processing networks? And this is already done. There is something called a generalized switch, which is a general model that subsumes pretty much all of this except load balancing. Load balancing is very similar to generalized switch, but the control is on the arrivals instead of service. And we have a recent work where we establish all the results that I showed you in the table in the context of a generalized switch. And I'm not going to say more about it here because I'm almost out of time. So this is my last slide. This is actually the same slide that I showed you at the end of part 1. This is the concluding slide of this tutorial. So the punchline that I want you to take home today is that drift arguments are simple and powerful. And we use drift arguments to study queuing systems, stochastic processing networks, and also stochastic approximation. And we use the stochastic approximation results for studying reinforcement learning algorithms. And in both of these different domains, we use these Lyapunov arguments to answer some very hard problems. In the case of queuing, switch scheduling was a long-standing open problem, which we resolved using Q parallel square as Lyapunov function. In the case of stochastic approximation, L-infinity norm contraction stochastic approximation was a long-standing open problem, which we addressed by starting with a quadratic Lyapunov function and smoothing it with a Moreau envelope. So in the case of queuing, unused service was the key thing to look at. In the case of stochastic approximation, in the simplest setting, binomial theorem was the important one. Later, we generalized it into smoothing. And for queuing, we worked with state space collapse to handle this unused service and to recognize the lower dimensional subspace in which the system lives in heavy traffic. And in the case of stochastic approximation, we basically smoothed out a norm when it is not smooth, like L-infinity norm. And there are, broadly speaking, 3 kinds of Lyapunov arguments. The first one, drift is negative. This is used in Foster-Lyapunov theorem. We used this to establish existence of steady state for queues. And the second one is drift is bounded by some minus f. And this can be used to bound this function f. And we use this by setting drift equal to 0 in stochastic processing networks. And the third one is when the drift is proportional to minus v. And in this case, we should expect exponential convergence in the absence of randomness. And we use this one for studying stochastic approximation. So with that, I end my talk as well as this tutorial. Thanks for your attention. I'm happy to answer any questions.